We're going to continue with our equations of motion for simple harmonic motion. We just did the displacement function, described why we established it the way that we do. So for this first graph you have on this page, the displacement function would use the sine term. But to get to the velocity and acceleration functions here, we're actually going to need calculus. Now, if you haven't done calculus yet, I wouldn't really worry about it, okay? All you need to know is that when you look at the change, when an object is changing its velocity, is changing its position, okay, per change in time, you're just looking at the sine curve and looking at how it changes, when its steepest change is happening, okay? And so we see here, when the position is 0, right, that's when this curve right here, that's when the curve is at its steepest, okay? So that's when we're going to have a maximum velocity. So that's where we start here. And we're basically looking at each point, how steep the curve is at all these points. We see here at 1/4 of the period, the function, it has a slope equal to 0, and so we're going to have the velocity function be equal to 0 at that time. Now, let's make that really easy. Boom. Velocity is the time derivative of position or displacement, okay? So what that means is that we're going to take the derivative of this sine function, and velocity is going to be equal to omega times x naught times cos omega t. All right? And that will be our velocity function. We see that our velocity function, interestingly enough, is 90 degrees or pi over 2 radians out of phase with the displacement. Okay, that's just an extra little piece of information for you to be thinking about, all right, when we compare these functions. When does the maximum velocity occur? Well, look at the graph, okay, or even consider the function, either way. But the two places that maximum velocity will occur here is when time equals 0. Again, this is only with the cosine function for velocity, all right, or when time is equal to the full period there. All right, that's another place. Or when the time is equal to half the period. Any of those are acceptable. Okay. To calculate the maximum velocity, by the way, so this is just max velocity. All right, we consider any of these times. At any of these times, we see v naught, the maximum velocity, is equal to omega times x naught. This is our little function for that. Okay? I apologize, sometimes I write in circles. Okay, next. We're going to consider the acceleration function. Again, for calculus, the acceleration is just the time derivative of velocity. So the acceleration is equal to negative omega squared times x naught times sine omega t. And you should see something familiar here. And I'm going to tell you what it is in a second. Now, the maximum acceleration, right, is going to be happening at t over 4 and 3t over 4 in terms of the period. But at those times when the sine is equal to 1, a naught will be equal to omega squared times x naught. I have dropped the sign here, okay? The reason for that is just I'm talking about the magnitude here. But we can rewrite either of these, all right? On the next slide I'll rewrite it here, just as v is equal to omega times x naught times cosine omega naught, or v is equal to v naught times cos omega naught, omega t, excuse me. And for acceleration, you can write it the same way. Okay. And it's important to note here that the acceleration is exactly out of phase with the displacement. That's important to know. That gets back to our defining equation of simple harmonic motion. So what does this equation here remind you of? There's a piece in this equation that you should see that looks familiar. Well, that piece is this right here. And that is just our displacement function. So you can replace this with x, and there it is. This is our defining equation from 2 videos ago. Of simple harmonic motion. Okay, I want you to go back to page 3 right now. At the bottom of page 3, I'm going to show you what the period is for simple harmonic motion. What we see here, we have 2 equations from 2 different proofs, all right, that relate the acceleration and the displacement. What we can get from these equations is that omega squared is equal to k all over m. Do a little bit of math here, all right? Omega is equal to the square root of k all over m. We keep going here, all right? 2 pi all over the period is equal to the square root of k over m. If we solve for the period, all right, what we end up with is 2 times pi times the square root of m all over k. I'm sure you can do the algebra there. So we see the period only depends on the mass of the object oscillating and the stiffness of the spring. That's really cool. So in other words, if we go back to my original video, it doesn't matter how far down I pull that spring, it's going to have the exact same oscillatory period. That should blow your mind. All that matters is the mass and how stiff the spring is. So that first question there, in those 2 examples, all right, the new amplitude is twice the original. The period is unaffected. However, if we double the mass, as they say in the second example, the new period, T2, is going to be equal to the square root of 2 times T1. If you look at that, look in the equation here, okay, you're doubling m. The factor by which you increase the period, therefore, would be the square root of 2, since you're doubling m. All right? And I'll quickly show you the math for that right here, okay? So T1 is equal to 2 times pi times the square root of m all over k, all right? And we'll call this m1. T2 is equal to 2 times pi times the square root of 2 times m1, since we doubled m1 all over k, okay? This is equal to 2 times pi times, I'm going to take the square root of 2 term out of here, all right? And what we end up with is this is just the square root of 2 times T1, like I showed you before, okay? That's it. It increases by a factor of the square root of 2. So that's a big, big, big idea right there for simple harmonic motion. There are alternative equations of motion. What if you start at the amplitude? Well, your displacement function, therefore, is going to look like the following. X naught times cosine omega t. Well, the derivative of that is going to give us v is equal to negative omega times x naught times sine omega t. And the derivative of that is going to give us, oops, a is equal to negative omega squared times x naught times cos omega t. Okay? When would we use these different equations? Well, all depends on the initial conditions. All right, kiddos? That's the trick. Do we start at 0 or do we start at the displacement? If we start at 0, you're using sine, and you use the equations of motion that match that. If you're starting at the displacement, the maximum displacement, the amplitude, okay, you will be using cosine and the functions that match that for their derivatives. I believe there's one extra section here that I have not covered. It's the alternate velocity function. So let me do that very quickly here, okay? The way that this is going to look, well, consider that our velocity function, if our displacement function looks like this, okay, then our velocity function will look like this. Let's go back to one of our first trig identities, shall we? Okay, and from here, I'm going to solve for cosine omega t. It's going to be equal to plus or minus the square root of 1 minus sine squared omega t. All right, and guess what? I'm going to substitute that in for my cosine term up above. So I get v is equal to plus or minus omega times x naught times 1 times, pardon me, times the square root of 1 minus sine squared omega t. And I'm going to distribute the x naught in here. And when I do that, I end up with x naught squared minus x naught squared sine squared omega t. And this is just the same as the displacement function squared. So I end up with something like this. And this is a big one. This is one that's very, very helpful to us. If we want to calculate velocity and we don't have the time, we can do that. We just need the displacement, the amplitude, and the angular frequency. Okay? Pretty cool. Next page here is an example. I think I'm going to fit it into this video, and this video will just be a little bit long. That'll be okay. All right, so from that graph, you have the amplitude. Well, the amplitude, x naught, is going to be equal to 6.2 centimeters. The period of oscillation you get from that graph as well. Pause this video if you want to do this on your own. I highly recommend that. Okay, again, pause this video if you want to try it on your own, then check your answers. This may be very similar to something I asked you to do in class. All right, so I'm just going to write down everything here because you can see on the graph that the period is 2.4 seconds, the time over which it starts to repeat itself. And this is approximately, the angular frequency is approximately 2.6 radians per second. Therefore, the displacement function looks like the following. Okay, the maximum velocity v naught is just equal to omega times x naught, which is going to be equal to 2.6 radians per second times 6.2 centimeters, and that is approximately 16 centimeters a second. And then we get the maximum acceleration as well. It's going to be omega squared times x naught. And let's see here. Plug in these values, and this guy is accelerating at 42 centimeters per second squared. All right, so high acceleration whenever we're dealing with these functions. At what times does maximum velocity occur? Well, maximum velocity occurs whenever the displacement is equal to 0. So for B, all right, it's going to be 0.0 seconds, 1.2 seconds, and 2.4 seconds. Okay? The condition is when B is at a max. All right? When A is at a max, this is when the displacement is also at a max. So 0.6 seconds, 1.8 seconds, and 3.0 seconds. The next question asks, determine the velocity of the object at 1.3 seconds. Use both formulas. What that's telling you is to use the alternative velocity formula and your velocity function from the displacement function. So we'll start out with that one. Since x, all right, deals with the sign here, we know that we're going to have our velocity function look like the following. Substitute all of our values in here. 2.6 radians per second times 6.2 centimeters times cosine of 2.6 radians per second times the time, all right, which is 1.3 seconds, will give us a velocity of approximately, and I'm rounding with sig figs here, 16 centimeters per second. Cool. Okay. Well, the alternative way of doing that is to say at time equals 1.3 seconds, okay, the displacement, x, is approximately 2.0 centimeters. Again, that's an estimation from the graph there. Substitute that in for our alternative velocity formulation. And we end up with the following. And I got, after rounding, about 15 centimeters per second. Now, rounding is an issue, reading the value off the graph is an issue. There's a couple of different reasons why these two values, 15 centimeters a second and 16 centimeters a second, are a little off. But given all those things, I am confident in the accuracy of both of my formulas. Now, wait, I have not finished here yet. This is negative, all right? How did I decide it's negative? Isn't it plus or minus? Oh, this is also supposed to be negative. I'm sorry. When you actually do that calculation. Okay, so this one, this equation, the negative is there because that's what the cosine returns to you. Here, it's negative. You have to choose it. It's plus or minus. But if you look at the displacement function, it's still moving in the negative direction. It hasn't reached its maximum displacement in the negative direction yet, so it's still moving that way. Okay? You're going to have to be able to look at these graphs and interpret what they mean. So look at the displacement versus time graph. Look at 1.3 seconds. Go down there. It's about -2 centimeters. It still has to head down to -6.2 centimeters, which means its velocity is going to be negative still. Once it gets back to once it gets to the displacement, the maximum displacement, the amplitude, that -6.2 centimeters, it's going to have to start heading in the other direction. At that point, that's when the velocity will start to be positive. Okay? Until then, it's negative, so that's why I chose negative here. That's something you actually have to choose, okay, when you're using that equation. And that is it for the equations of motion for simple harmonic motion.